All right, let's jump straight into this explainer. Today, we're exploring the absolute foundational building block of artificial intelligence, the single artificial neuron. If you really want to understand how massive, complex, deep learning models work under the hood, you've got to start right here. We're going to build a perceptron from scratch, watch it learn, and then, quite dramatically, watch it break. But before we get into the nuts and bolts of the math, we're going to unravel a true historical mystery. We're looking at the exact mathematical limitation that caused the very first AI winter. Just imagine an entire field of booming, optimistic research coming to a grinding halt, all because of one specific geometry problem. Crazy, right? Well, that's exactly what happened. And by the end of this explainer, you'll know exactly why.
Section 1. The simplest neural network. So, to understand that historic failure, we have to start at the very beginning. We're stripping away all the hidden layers, all the massive data sets, and focusing purely on the core mechanism of decision-making. Enter the perceptron. A perceptron is the simplest possible neural network. It's just a single artificial neuron. You can kind of think of it as a tiny, isolated decision engine. It takes in various inputs, processes them together, and spits out a strict binary decision. It really is the fundamental atom of machine learning.
Geometrically, you should imagine this as nothing more than a single straight line slicing directly through a 2D space, basically separating data into two distinct camps. This is literally the single most important idea to hold on to today. A perceptron is simply a linear decision boundary, nothing more. Everything on one side of the straight cut gets classified as a 1, and everything on the other side gets classified as a 0. Now here's the mechanical sequence of how that cut is actually made, broken down into 4 simple steps. First, the neuron takes in inputs. Second, it multiplies each of those inputs by a specific weight, which essentially assigns an importance level to each input. Third, it sums all of those weighted inputs together with a baseline value that we call a bias. And finally, it passes that total mathematical sum through what's known as a step activation function. And that step activation function? It acts as the ultimate judge. If the mathematical sum of those inputs, weights, and bias is 0 or greater, the neuron fires off a 1. But if that final sum is less than 0, it stays quiet and fires a 0. It's a harsh, immediate threshold. There's absolutely no middle ground here. No maybe, just yes or no. Section 2, the perceptron learning rule. Having a decision boundary is one thing, but how does it actually learn where to put it through trial and error? Well, unlike the complex, smooth gradient descent you'd see in modern networks, the original perceptron is almost delightfully stubborn. The weights only shift if the prediction was actually incorrect. Think about that. If the perceptron predicts right, absolutely nothing changes. If it ain't broke, don't fix it. But if it guesses wrong, it forcibly shifts the weights and bias in the direction that would have made the correct answer more likely. Now, this leads to a crucial mathematical guarantee known as the perceptron convergence theorem. This theorem states that this simple update rule will always converge. It will always find the perfect separating line eventually. But there's one massive, non-negotiable condition. The data must be linearly separable. If you cannot draw a perfectly straight line between your two classes of data, this entire theorem falls apart completely. Section 3. Solving and/or. Let's see this in action with a classic success story, the logical AND gate. We're going to feed the perceptron simple binary inputs, 1s and 0s, and see if it can learn the basic logic of an AND gate, where the output is only 1 if both inputs are 1. As we step through the inputs, notice what happens when the prediction is wrong. Right out of the gate, on the first row where the inputs are 0 and 0, our perceptron accidentally fires a 1. Because that prediction is wrong, the bias forcefully updates to -1 to correct the error. By the time we hit the last row, the target is 1, but our network predicts 0. Wrong again, so the weights for both inputs push up by 1, and the bias adjusts again. It's literally learning from its mistakes, step by step. And you know what? After just a few passes over this dataset, the separating line settles perfectly. The weights converge to 1 and 1 with a bias of -1.5. If you do the math, only the inputs of 1 and 1 yield a result greater than 0, which gives us our correct target. The straight line has successfully separated the data. The AND gate is fully solved. The logical OR gate is just another easy win for the perceptron. It works in the exact same manner. Geometrically, it just requires a smaller bias magnitude since fewer points need to fall on the negative side of our straight line. So there we have it, a working artificial neuron that can successfully learn basic logic. Section 4. The XOR limitation.
All right, let's keep this momentum going. We just conquered and or. So now let's tackle exclusive or XOR. In an XOR gate, the target is 1 if one input is 1, but crucially, the target is 0 if both inputs are 1 or if both are 0. We're going to plot these 4 points on our 2D plane, 2 ones and 2 zeros, and let the perceptron go to work drawing its line, applying the exact same learning rule that just succeeded seconds ago. But when we actually run this, something wild happens. The line oscillates wildly. It bounces back and forth, completely failing to settle on a solution. You could run this for 10 epochs or 10,000 epochs. The line will never stop moving. The training has completely and entirely failed to converge. To understand why it's panicking like this, let's compare the geometry. For our easy wins and/or, the data points sit in neat, linearly separable clusters. You can easily draw a single, straight ruler line between the ones and the zeros. But think about XOR for a second. The ones and zeros are arranged diagonally from each other. It creates this impossible checkerboard-like geometry. And this brings us to a really harsh mathematical reality. No single straight line can separate them. Seriously, try yourself on a piece of paper. You just cannot separate those diagonal points with one straight cut. This isn't a glitch in our training loop. It isn't a bug we can fix with more data. It is a fundamental mathematical representational limit of the perceptron itself. Because the perceptron is limited to a single linear boundary, and XOR requires a nonlinear boundary, the single artificial neuron is completely powerless here. Now, this precise failure wasn't just a quirky lab result, it actually changed history. This limitation was rigorously proven and published by Marvin Minsky and Seymour Papert in their famous 1969 book, Perceptrons. They laid out the cold, hard math showing exactly why a single-layer perceptron could never solve XOR. And this single limitation was so devastating, so deeply discouraging to the scientific community that funding basically dried up overnight. It triggered a massive slowdown in AI research for over a decade, an era we now call the first AI winter. As we wrap up this explainer, just think about how monumental that roadblock was. The single neuron was fundamentally broken for this task. But ask yourself this. If one straight line inherently fails to capture complex diagonal relationships, like XOR, how might we stack multiple lines together to compose a nonlinear boundary? This exact historical crisis, this specific geometric failure, is the entire reason we had to invent hidden layers to save neural networks. And that brilliant breakthrough, well, that's exactly what set the stage for the modern AI revolution.